very interesting 9 presentations. So at the end of 5 minutes, I'll show the 2-minute sign. And at the end of 7 minutes, you need to stop. And if you see me standing, I come out, that means you really need to stop. Okay? So first speaker, Charlie White from University of Toronto about visual influence on summer ozone episode. Please.
Good morning, everyone. It's my honor to kick off the final day of IGC9. And I'm going to somewhat boldly do it with a presentation that contains very few results from GeoSChem itself. This is work that I've been doing with my advisors Dylan Jones and Paul Kushner at the University of Toronto. And it focuses on identifying ozone pollution episodes in North America summertime, but in a way that isolates the role of meteorology rather than emissions. So to preface this, I'll say that there are reasons to focus on acute ozone pollution episodes besides their contribution to long-term exposure to ozone. We have evidence that acute ozone pollution can immediately increase incidences of acute respiratory illness. And for vegetation, we have some evidence that short-term acute exposure does more damage to vegetation than the same dosage over a longer time period. So the data that I'll be looking at for this analysis consists primarily of North American air quality monitors from the AQS and NAP system in the United States and Canada, respectively. These measurements are all maximum daily 8-hour averages in the summertime from 1980 to 2018. And to take advantage of using the entirety of both of these networks in the same analysis, we need to somehow subdivide the stations. And we've done that here by using a clustering algorithm that is based on the timing of extreme ozone days at each individual monitor. To look at meteorology, I'm going to break ranks a bit and look at the ERA interim reanalysis. And we're going to focus on subseasonal timescales because at these timescales, meteorology is most important rather than longer timescales, which might be more related to long-term emissions trends. And so as an illustration of how we will isolate these subseasonal timescales, we can look at this time series from an individual monitor in Georgia, which has data going from 1991 to 2015 or 2016. So we can see that due to emissions, there's over this time period a drop in summertime concentrations by about 20 parts per billion. And to remove seasonality, that long-term trend, and interannual variability, we've simply applied a 90-day low-pass filter, which you can see in this orange line. There's some weird jumps. That's just because it's truncated to summer days only. Now, after subtracting that low-pass filter time series, we can still see that, we end up with this anomaly time series in blue. However, there's a residual effect of long-term trends in emissions, which is that we have reductions in the magnitude of variability of ozone over this time frame. And so to account for that, when defining an extreme threshold for ozone, we've applied a rolling 95th percentile calculation. And so you can see that the extreme threshold actually decreases over time. So actually going back here for a moment, all the moments at which ozone exceeds this red line are identified as an extreme day at that station. So we have a Boolean time series of extreme or non-extreme days at every single monitor. And we use a similarity metric between any pair of stations as input to a clustering algorithm. And the results of that clustering algorithm are shown here. And so we can see that we have some fairly geographically distinct clusters that are based only on extreme ozone events. And to finally define ozone episodes in each of these regions, we're going to focus on the time series of daily 95th percentiles in each cluster. So first, I'll draw your attention to the northeast cluster, since that's what I'm going to be talking about. To illustrate this definition, we look, the red line here is the 95th percentile of ozone. It varies up and down. There's an extreme threshold here defined by the long-term mean plus standard deviation of the 95th percentile. And when we have a 3-day exceedance of that threshold, this is an ozone episode, and we allow for some short dips below the threshold without breaking the ozone episode into multiple smaller ones. So the results of doing this for the entire time series in the Northeast region looks like this. So all of the orange and red dots are ozone pollution episodes. And what we can do to figure out what the typical meteorology is for these events is average over the first day, or average over all the ozone episodes, centering on the first day of each. Okay, so if we look at temperature, we can see something that might not be intuitive because you might expect very extreme temperatures during ozone episodes, but in the Northeast, we can see for the first day of an ozone episode, temperatures are extreme just outside the region, but not in it. In the Southeast region, we don't see any particular temperature enhancements. If we look at humidity, another expected driver of ozone pollution, we can see that in the Northeast, we have some drier than average regions and some wetter than average regions. So it's not clear what the dominant effect is. Whereas in the Southeast, we can see dry conditions all throughout the region. And if we want to put our attention higher in the atmosphere, we actually see some large-scale wave trains. So this is indicating that there is a large-scale structure associated with these ozone episodes. And in fact, we can see that these large-scale structures develop up to a week in advance in the composite of the ozone episodes. And so this hints that there might be some possible predictability, that enhancements that we can gain. So finally, or not, so if we look at averages across each region for these meteorological quantities, we can see that in the Northeast, we have some expected behavior where ozone rises in phase with temperature. However, humidity is also strongly correlated, which might be unanticipated. In the Southeast, we can see low humidity is significant during ozone episodes, and temperature actually peaks after ozone does, and ozone is decreasing when temperature peaks, also unintuitive. So the point there is that phase relationships change from region to region. And so the next step is to investigate this in GeosChem. I'll be running a nested North America simulation. Here are some preliminary results from a 2x2.5 simulation where we can see the model capturing an ozone episode that was identified in the analysis. And so in summary, clustering ozone monitors by extreme days identifies 7 distinct regions in North America. We see a lead time of about a week for the large-scale circulation patterns that get identified during these events, and the phase relationships of local meteorological quantities during these ozone episodes varies from region to region, which might hint at differences in the importance of processes, chemical processes from region to region. Thank you.
Questions?
Hi, have you considered the role of the Bermuda High in how that could affect the Southeast US?
I have not explicitly considered it. I know that it shows up in some analyses that focus on longer timescales.
Yeah.
And so I'm curious, I would be curious to see if it shows up when you look at these shorter timescale events, or if it perhaps modulates the patterns of variability such that the event, though they're more common when you have the Bermuda, in certain phases of the Bermuda High. But I'm not exactly sure.
That's great.
Yeah.
One more question?
Hi. I was wondering, in the cluster analysis, how you decided on the number of clusters you use, and whether you think your results might differ if you had maybe a larger number of clusters that might be a little smaller, basically.
Right. So there's a metric for there are various metrics for evaluating the quality of clustering. I used one that's called the Kolinsky-Haberaj, I forget the exact name, analysis. It's basically comparing the within group sum of squares to the between group sum of squares for all the clusters. And I basically chose a local maximum in that index that happened to correspond to a priori knowledge about regions of ozone variability. Going to larger numbers of clusters, they get a lot messier, less well-defined, and yeah, kind of more dispersed. So it's not as useful for analysis.
Thank you, Charlie. We have to move on. Next lady from the University of Houston talking about ozone in San Antonio.
Good morning, everyone. I'm Wei from University of Houston. My topic is influence of regional transport on San Antonio ozone internal ability. So San Antonio is the second most populous city in Texas with warm climate, booming industry. It also suffers from air quality problems. This figure shows the ozone design value in San Antonio is about 7 ppb in last 14 years. In 2018, San Antonio was newly designated ozone non-attainment by EPA. So to better understand ozone, TCEQ funded a field campaign in May 2017. This figure shows the ozone seasonal trend based on the days that the MDA ozone exceeded 70 ppb. You can see May is ranked highest. So San Antonio field campaign is collaborative work of UH, Rice Baylor, St. Edward, led by James Flynn from UH. We have 2 campaign sites, Travelers World and UTSA, with instrument measuring ozone and other species. And we focus on the model simulation for ozone. We use GeoFP data and conducted a nested simulation in North America. For the anthropogenic emission, we scaled the inventory to 2017 and reduced NOx emission in East US by 50% to have an unbiased ozone simulation. So this time series shows the model evaluation of ozone at Travelers World. You can see the model gets the variability very well, but not the peak values. You can see some days very high, some days low. Overall, the model overestimates the ozone, especially during nighttime. Another thing that the model surprised us is the vertical distribution. You can see the model matches very well with the ozone sum data, which is really good result. So this is the 13 years mean wind and geophysical height in May, which illustrates the regional transport very well. You can see the Bermuda high anticyclone can pick up emission from Central America, South Mexico, and then mix up with the air mass in Gulf region, and then goes into East US. And we call this marine air intrusion. North Pacific high is near West Coast here, and these 2 anticyclones can converge in Mexico region, and this can really influence the transport. The observation also shows the marine air intrusion events. Here we choose chloride and the cesium sulfate as the indicators of marine air. You can see the black line is observed chloride, the red line is simulated cesium sulfate. As you can see, the model, I guess 2 peaks, which means the model can capture the marine air intrusion events. Another thing is both the observed and simulated ozone is anti-correlated with chloride, which indicates the marine air intrusion is associated with the low ozone. So now we know that the regional transport can influence the daily variability, and the model can get that. So we also assume that it can also influence interannual ability. So the question is, to what extent does the regional transport influence also interannual ability? So to solve that, we applied this passive traces simulation because it is very fast and good for long-term simulation. The downside is it does not include chemistry. Our group member Stanley Wang has used this method to analyze the transport of air emission in Central America. In this study, we conducted 13-year simulation from 2005 to 2017. We designed several tracers to cover different regions, and then group these tracers into 4 categories. Marine tracer include these tracers from south, continental tracer from north, and in-state tracer covering Texas, and the Mexico tracer. After simulation, we checked the correlation between MD ozone and continental tracer, marine tracer, continental managed marine tracer, respectively, and then found continental managed marine tracer had the highest correlation. So we defined continental managed marine tracer as regional tracer, and this should be a better predictor of the ozone variability. And then we applied a linear regression model to ozone and other species and found an equation like this. You can see regional tracer and the in-state tracer are statistically important, and all the tracer in combination can explain nearly 60% of the variability. And the regional tracer alone can explain about 20% of the internal variability. And then we apply the same way to Houston. Only regional tracer stands out here, and all the tracer in combination can only explain nearly 40% of the ozone variability, which indicates a more complex circulation pattern for a coastal sea. But the regional tracer alone actually can explain more than Centennial. So at last, we checked the transport pathway for each tracer. East USA mainly traveled at the surface. Marine tracer and the Central USA tracer are from south and north, respectively. And the Mexico tracer and the West US tracer can be lifted up to around 3 kilometers. Mexico tracer is drawn at all levels from south to north. West USA is drawn at high levels from west to east and then goes down in the east and travel back at the surface. This vertical profile of West US tracer shows vertical circulation around there. Oh, sorry. So in conclusion, the GeoSky model can capture the model of the ozone variability and the vertical distribution and the marine air intrusion. And the regional transport can explain 20% of the interannual variability of ozone. Thanks all the participants in the Centennial field study. Thanks TCEQ for the funding opportunities. That's all. Thank you. Okay.
It seemed in your analysis that the in-state tracer had negative correlation with ozone.
Yeah.
Does this mean that ozone pollution is coming from outside Texas?
Actually, one reason is because maybe the cost resolution of the model. Second, maybe we check the wind. Actually, the south wind is more frequent than the north wind. So that's why maybe it's a mass correlation. Yeah.
Could you explain the dynamical features in terms of a large scale like Bermuda High? Do you think it would be more appropriate to look at sort of smaller scale features like low level jet and features like that? I realize that they're dynamically linked, but.
Yeah. Actually, we're studying the circulation pattern in Houston. Actually, low data is a really important reason for the ozone. But here we only check the regional transport. Yeah.
Let's thank Ray again.
Thank you.
Next speaker is from Suni Albali. He'll be talking about long-term trend in particle number concentration in the U.S.
Okay, thank you. So we all know in the last 2 decades in the U.S., SO2 and NOx emission decreasing a lot. SO2 you can see by a factor of 4 or more. We know PM2.5 have been decreasing as well. So question we wanted to address, what about the particle numbers, how they change in response to these emission reductions? So to study this, we use GeoSky with the APM we run the model for the first past 18 years, and we listen just extend to the past 30 years, and we try to focus on the numbers. So APM, we deal with the size resolved alpha microphysics. We separate the particle into second particles and also the primary particle, which you direct emit. In terms of the particle number, second particle are important and dominant in a lot of places. So we need to get the second particle right. We can never get in the detail. Second particle, first you need to form from the gas phase. Then they can grow through the uptake of a bunch of the species, including organics. In order to get the number right, nucleation is also important process. So in this study, we used a recently developed, we call it ternary ion-mediated nucleation, involves sulfur acid, water, and ammonia. And this model calculated the dependent nucleation rate on a bunch of the parameters. What is shown here is nucleation rate as a function of the ammonia concentration. So I just want to point out two things. One, ammonia concentration is very important and have a strong effect on the new particle formation, even at a sub-ppb level, at about 10 ppt, you'll see a significant impact on the new particle formation rate. Another, what's the difference between these two is the ionization rate. So when ion production change, new particle formation rate also change. So we consider all these in the simulations. For the US, so we look at the trend in the past 18 years. Again, that's SO2 concentration in the low troposphere. You'll see annually decreasing by about 8 to 9% due to reduction. It's a linear trend. As a result, actually, ammonia emission not changing much, but as a result of the SO2 reduction and NOx reduction, if you look at the scale, it's a little different. It's a percentage increasing, especially in the northeast part. Ammonia concentration actually increasing, and it's about 10 to 15%. That's associated with the equilibrium, nitrogen and ammonia. Because of the SO2 reduction and NOx, so that's compensated the new particle formation. So what is shown here is the linear regression of the new particle formation rate is ternary ion-mediated nucleations. The color scale is different, 0. Actually, this is 0. So you see a decreasing in the west part, but in the east part, new particle formation rate does not change a lot. So that's the effect of ammonia compensates that. As a result of all these changes, the particle number trend it's decreasing, but it's around a few percentage linear per year. Then we also can calculate CCN. It's about a 3 to 4% linear annual change. And in our model, we also calculate the CDNC, cloud-droplet number concentration change over the US in the low troposphere. It's changing in the order of the per year, it's about a 2 to 3%. So we can see the level of decreasing is much less than the SO2 projected SO2 reductions. And one thing, this is number change. So we try to look at what's the implications. One application we use, we try to study the health effect. So we focus on northeast US, actually focus on New York State. In each grid box, we calculate the size distribution. So that's the size distribution model calculated from the 2000 to 2017. And from this size distribution, we can calculate all the CN, CCN, optical properties. In this particular thing, we look at the ultrafine particle number effect on health. So that's the particle number. You can see events. That's a peak. And these are the yellow one is observation available at this clinical state park. So model generally captures these events. So you have not a PM pollution event. It's an ultrafine, usually the clean days. And we use this and collaborate with the School of Public Health, look at the health data and try to find the correlations. So that's the health effect we try to study, and the health information is from all the hospitalization. So if the people go to the hospital and they are so serious, they have to be hospitalized, then we compare and use this ultrafine particle number concentration associated with this. And we also calculate PM 2.5 from these side distributions, and we also compare that as a double check. So these are the preliminary results we are looking at. What is shown here is a lag. So you have a delay of the response. That's the present day and a 1 day delay. So past the 3 days, past the 0 to 2, and that's delay impact associated with health, excess health impact. And that's the excess risk, that's the inter-quarter range. So we look at about quarter million of the case, and we looked at the impact. Actually, we found a strong signal of the ultrafine particle number. That's not associated with the mass because ultrafine particle mass are small, but the number is high. That's the PM 2.5. PM 2.5 also have effect, we all know. And the magnitude is similar. So that's the point we want to make. So ultrafine particle also important on the health. We also look into the aerosol indirectly diffusing and directly diffusing. What is shown here is for the directly diffusing, we know the AOD is important. And we compare the model simulated AOD with the NASA GSFC AeroNet side. You see the decreasing in the AOD, and that's also pretty clear. And actually decreased by factor 2. That's associated with the mass decreasing. And if we look at the aerosol directly diffusing change over the US, that's only over the US, not global. You see quite a significant decreasing in the directly diffusing from 2000 to 2016. A factor more than 2 directly diffusing because of AOD change. But if we look at the indirect effect, that's associated with the number, CCN and CDNC. That's a direct we just showed earlier. You see the difference is quite significant. So indirect is decreasing, but not as significant because the number decreasing is not as significant as the AOD. So the number. So to summarize, we looked at user just chem APM, looked at the long-term trend. We focused on number, and we found the number is decreasing, but not as significant as the mass or SO2 reductions. And we found the association of the ultrafine number with the health. AOD is decreasing by a factor of 2, and directly diffusing also decreasing over the US. Indirectly diffusing is decreasing, but it's not as much. So that's a summary, and I will show a bonus kind of the slide. That's our simulation in the past 30 years. Particle mass needed number diameter change. So we know in a lot of situations you need to assume particle size, especially in the bulk, and let's see the signal variation in the global. So I will stop here, and I will happy to take any questions. Thank you.
Thank you.
So this is wonderful, but I'm curious if you can begin to validate any of the trends in radiation at the surface using long-term monitors in the US or cloud cover, given changes in CCN. This has been a big puzzle in the community. I'm wondering if you have any ideas for how to solve that.
Yeah, I think that's a good point. Yeah, I think we definitely, in our model, we calculate the surface flux. And their surface sunlight measurement, actually solar radiation measurement, we can compare with that.
There is a site in New York that you can
and also for the indirect effect, we look at the Moody's CDNCs, they can derive that. Now you use the cloud property. And we look into that as well. Try to look at the trend.
You have time for questions.
I was wondering, what's the relative importance of primary emissions for ultrafine particles, or is it just nucleation?
In terms of number over the US, most is dominated by the second particle. Primary particle account in terms of CCN, based on our model calculation, about depending on which seasons, 10 to 20 or 30% is the primary, and 80 or about 80 is the secondary.
So besides emission changes, does temperature or relative humidity trend affect the nucleation event? So assuming the model should be able to capture that?
Yeah, model consider the effect of temperature, relative humidity, and also the surface area change. The temperature, relative humidity not have a strong impact because the trend is not that, but during specific year could have an impact. We didn't look into that, but in the long term should not have a strong effect, delay on nucleation. But I'm not sure how that may affect emission. if they have an effect emission on the biogenic, that could affect the growth of the particle.
More questions? Thanks.
Okay, thank you.
And we move on to the next. Yes, John from University of Iowa, PM 2.5 forecast.
Hi, everybody. And today I'll be sharing some of our work to improve surface PM 2.5 forecasting in the continental United States by incorporating satellite data, chemical transport models, as well as ground observation. As some of you may have known, the U.S. EPA aeronaut programs provides today and tomorrow air quality forecasting for key air pollutants such as ozone and PM 2.5. And these forecasts are primarily made from major metro areas and less information available for the rural areas. And in support of this forecasting system, there are about 600 ground stations that provide near real-time hourly PM 2.5 mass concentration, so as these blue dots on the map. As you can see, they are not evenly distributed, with more like in the eastern and the western United States, and that's available in the Central Great Plain and the Rocky Mountains, like the rural areas. Additionally, there are some like the improved network provides daily PM 2.5 measurements, so as these right triangle size. These measurements are available like every third day, so they are roughly about 10 samples per month, and they are mostly located in the national park and the wilderness areas. They do provide like very valuable information for the PM 2.5 levels in the rural weather because of the temporal resolution of the data, so it's hard to support air quality forecasting. So the question here we ask is, how could we improve the surface PM 2.5 forecasting, especially in the rural areas in the United States, with all the data we have? So to address this question, here we establish a framework to provide some bias correction technique that's applicable to air quality system, forecasting system. And here, basically, we take a multi-model, multi-LD approach, as well as some statistical methods. For modeling, we use 3 models, a GeoSCAM, WRF-Chem, and a CMAC. For LD products, we use LD, a modest LD on board Terra, Aqua, as well as WIRS, and we also use these hourly and daily ground measurements. So in the next few slides, I'm just going to demonstrate this framework. So first of all, we did a case study for June 2012 to run model simulations, and this panel map shows the model simulated monthly PM 2.5 evaluated against these 600 hourly EPA measurements. As you can see, in general, the 3 models could capture the spatial variation with higher concentration in the eastern United States and lower concentration on the west. However, all these models have bias. In this case, they underestimate the ground observation. So our first step is to correct the model bias for any model grids that are co-located, with these 600 ground observation. So we use a common filter technique. The idea is we use today's forecasting bias as well as the ground observation available to correct the forecasting bias for tomorrow. Then we can update the model forecast. And here's the Taylor diagram, so the model evaluation performance. And here is the ideal point. The closer any dot to this point, the better the model performance. So first of all, this 3 circles shows the raw model performance for the 3 models, and the triangle set shows the corresponding common filter corrected model performance. And these last right circle, these 2 dots shows the ensemble model performance. Here, ensemble means simply averaging these 3 models with equal weight. So as you can see, the common filter corrected model performs better than the raw model, and overall, the uncountable common filter provides the best performance. So after we have correct model bias for model grids that have hourly ground observation, so the second step is to propagate this bias cross information we get it from common filter to any model grades that don't have that don't have ground observation available. So here we use another approach, successive correction method, to correct any model grades that are in the radius of 125 kilometers away from these hourly ground measurements. So by doing so, we can see we are able to correct a more like a bias in these yellow areas. They are clustered around all these hourly ground measurements. As you can see, there are still places like in the Central Plain, the Rocky Mountains, that are not be able to covered. So here I briefly show some of the ICM evaluation results. So on this map, as the 600 sets, so the triangle sets are used for evaluation. So here we use CMAC as an example. So the scatter plot on the left shows the raw CMAC performance. On the right shows the ICM corrected CMAC performance. As you can see, this method can improve correlation and reduce RMSE. So our last step is to correct a model bias for any model grades that don't have measurements in 125 kilometers, but do have measurements between 125 to 300 kilometers. This is where LD will come into play. And by doing so, we can pretty much, just still tiny bit part, but we can pretty much cover the whole continental United States to do model bias correction. And the idea here using AODs is to take advantage the AOD spatial gradient between the model grade and the ground observation. That way we can transfer the bias correction information we got from this ground measurements to the model grades. And here I show some like preliminary results. Here we use this 26 triangle sets from improve as evaluation, and then we scale the model infer PM 2.5 from this blue circle, which provides the hourly groundments. And here shows the results. So on the top, we shows we still use CMAC as example, the raw CMAC performance, and the bottom shows the AOD corrected CMAC. As we can see for the whole month of June, we can see a decrease in the mean bias, even though the correlation didn't get improved. So we think using the AOD spatial gradient and combined with these common filter corrected bias information can help us to provide some to scale PM 2.5 in rural areas. So it is promising, but a lot of work still need to be done. So I will leave it there, and thank you very much for listening, and I'm happy to take any questions. Oh, okay.
You use like geochemical transfer model.
Yeah.
But this kind of model cannot do forecast.
Yeah, but now WRF GC is available. Yes, well, you're right. At that time, like we use you. Yeah. That's just back then we started the work. We just use it as a demonstration tool, so we can use different model to do ensemble. But now with WRF GC, I think it's possible to do forecasting using geochem chemistry.
Okay.
Thank you for asking.
Oh, yes.
So I was wondering, so you said you're using a common filter at the places where there's surface station.
Yeah.
But you're doing a different kind of statistical correction. I was wondering, you could just use a common filter everywhere if you kind of characterize your error correlation between the model and your observations properly, and just do kind of a common filter simulation everywhere. Did you consider doing that?
That's a good thought. I haven't thought about that far yet, but yeah, that's a good point, definitely.
We could still have time. One more question. Aaron.
Yeah, I'm a little bit interested in the way you're handling the improved site. So when you have the 1 in 3 day sampling, are you developing the correlations based on that on longer timescales, and then using the longer timescale correlations with that in AOD for daily predictions, or are you developing day-specific correlations when you have improved?
Yeah, that's a good question. So the improved sets, because they provide daily measurements, we use it for evaluation. We currently only tested for 1 day. We have improved measurements, but then in the future we can do more like testing. Yeah.
Thank you, Jessie. Yeah. So next speaker is Cass Carter from MIT about biomass burning aerosol.
Thank you. So again, my name is Tess Carter, and I'm a PhD student working with Colette Heald at MIT. As my title suggests, we're looking at biomass burning aerosol emissions in North America. And there's particular interest in this because of the We Can campaign that happened last summer, as well as the upcoming Fire XAQ, both of which predominantly focused on the Western US, which is consistent with the literature suggesting that there's increased fire intensity and extent shown there. However, there hasn't been a systematic analysis of the fire emissions inventories in North America, which would be particularly useful. So on that note, inventories represent fire emissions quite differently with different outcomes. And there are two major theoretical approaches to making these inventories. The first is sort of a more traditional bottom-up, and we look at two inventories that do that approach, GFED4 with small fires and FIN. In addition, there's sort of a more new approach using fire radiative power, and we look at two inventories that take that approach, QFED and GFAS. Historically, the majority of studies used GFED, and it's only been recently that we've had these other suite of inventories to compare with. However, each of these inventories, with all of these different variables that create them, has underlying uncertainties that can be quite significant. And so most modeling studies only choose one of these, though, and don't look at the uncertainty associated with fire emissions, which I will show is actually quite significant. So jumping right in, here I'm showing the range in total annual emissions across 11 years from 2004 to 2014. To orient you, and this coloring will remain consistent throughout, GFED's in red, FIN orange, QFED light blue, and GFAS dark blue. And what I'm showing here is Boreal North America, so that's Alaska and Canada, and we see a range on the top for black carbon of roughly 4 or 5, and organic carbon has a similar range across inventories, but the relative magnitude shifts, with QFED emitting the most black carbon, but GFAS and GFED sort of pulling ahead for organic carbon. We also see significant interannual variability as evidenced by the height of the box plots, which is consistent with our understanding of Boreal emissions. If we then look at the contiguous US, we see similar trends in relative magnitude across the inventories, with QFED largest, although the spread increases for black carbon to roughly a factor of 13 across the inventories, with the spread for organic carbon still around 5. And that interannual variability collapses for all except QFED, which, as I mentioned, is also significantly larger. I've also included an analysis at the global scale where we also see significant ranges, although that's not the focus of this talk. So here, I'm showing North America in emission factor space, which corresponds to the underlying vegetation masks used. And we're curious about the role of emission factors since there's a large emphasis on the measurement of those in the spread of emissions across years. And we do see significant variability, especially in the Boreal area where we would expect large fires. FIN shows lower values across both species. And then also black carbon, GFED shows much larger values. So if we're curious about the role of emission factors in this variability across inventories, what we can do, and what I'm showing here for just Boreal North America, is actually dividing off emission factors to get at the underlying dry matter burned. And so these are the same conventions I just showed for the box plots, but the top plot is dry matter burned across inventories, and we see a similar factor of roughly 4 compared to roughly 5 for black carbon, and this trend carries through across other regions as well. So this suggests that it's the underlying dry matter burned as opposed to emission factors that's driving this spread. So because we do see such a large spread across emissions in the inventories, we compare model simulations with GeoSChem driven by each inventory to observations to see which drives us closest to observations. And so what I'm showing here on your left is the Boreal region of the ArcTask campaign, and I've pulled out those points most influenced by fires by filtering for the top 25th percentile of acetonitrile. And so what you can see here, I'm only showing organic aerosol because black carbon looks very similar, but you can see GFED in red matching observations in black quite well, with FIN in orange falling away and actually looking like simulations with no biomass burning in gray. And then you can see the two blues, which are GFAS and QFED, looking decent to 3 kilometers and then overestimating to the surface. So then if we look at the DC3 campaign, which is characterized by different types of fires, we can see that black carbon and organic aerosol have sort of divergent trends. On top for black carbon, we see 3 of the inventories, GFED, FIN, and GFAS, matching observations quite well, with QFed significantly overestimating. And then if we look at organic aerosol, those 3 inventories fall away while QFed continues to overestimate. So the takeaway here, we've also compared with improved surface data as well as MODIS AOD, and these trends remain consistent. That GFED and GFAS generally match observations fairly well, with FIN biased low and QFED high. So if we're interested in how emissions variability and uncertainty impacts air quality estimates, we can look at annual mean biomass burning aerosol only surface concentrations of PM 2.5. And so that's what I'm showing here with simulations driven by each inventory. And we see significant differences carrying through, especially in regions where the biomass burning component of PM 2.5 is already exceeding WHO annual mean limits. In this case, that's 10 micrograms per meter cubed. So anywhere you see warm colors of yellow or red, which are quite variable across inventories, that's significant. And so this provides evidence for the fact that when we run air quality studies, we should be thinking about the fire emissions uncertainty associated with that. And then finally, we also are curious about how these differences carry through for direct radiative effects. Here I'm showing annual mean values for 2012. And we see all those differences in emissions and concentrations carrying through for Boreal North America and the contiguous US. To give you a feel for the global range shown here on the far right, I draw your attention to the bottom right, which is the organic aerosol top of atmosphere direct radiative effect across inventories. That number is roughly minus 0.25, which is roughly equivalent with the IPCC number and other literature estimates for the aerosol direct radiative forcing. And so this suggests that the uncertainty in our understanding of fires is roughly comparable to the anthropogenic impact on aerosol radiative effects. So to conclude briefly, the 4 inventories that we've looked at in the versions we looked at, to be clear, perform differently depending on species and location, with large ranges in North America. Underlying emission factors are important, but it seems like dry matter is actually driving the differences. Again, over North America, model simulations with GFED and GFAS match observations best. We also looked at including more SOA from fires. I didn't have time to talk about that here, but I'm happy to talk more. There seems to be regional differences. It improves observation model agreement in some areas, but not in others. And then finally, and perhaps most importantly, air quality and climate studies should consider and assess fire uncertainties. So thank you. Happy to take any questions.
Look at all of the gas phase species.
We looked at CO briefly, and it follows the interannual variability we showed for organic carbon, but we haven't gone any into any more depth.
So you basically identified burned area as kind of the main culprit here. So do you have any thoughts on what different inventories you might be doing right or wrong in that respect, or what's driving those differences?
Yeah, I guess I would clarify it's actually dry matter burned and not burned area. But what we've looked at, I guess, for FIN and QFED specifically, QFED actually scales up to AOD. So they have sort of biome-specific factors and literally are just scaling up total emissions to match AOD. So we think that might be contributing to the overestimate. And then FIN, in sort of its development, takes sort of a coarse assumption of just active fire counts and then assuming a burned area, which is pretty general across all vegetation types.
I thought I hear you say that GFED is actually relatively higher in terms of OA, but then in your DCA comparison, you show that GFED has a larger bias in OA relative to BC. Is that because of the difference in emission factor for small fires? Or?
I think when I said it's relatively larger, that was for Boreal North America, and so that's where we see it matching observations quite well.
Okay, if not, let's move on. Thank you.
Oh, Tina had a question.
Yeah. Oh, that's one more question. Sorry.
Yeah. So, it's not the focus of your talk, but globally, you showed that for BC, the difference between QFED and the other inventories are about 2 and 3 times higher than the other inventories, but for OC, it's about only 1.5 times. And I'm wondering if you know why that is, because the scalings for OC and BC are the same in QFED and OC scale.
Yeah, as I mentioned, we haven't gone into the global analysis quite as much, but we think that the spread and emission factors might be smaller. But yeah, we could definitely look into that more in the future.
Thank you. Next speaker, Amir Suri from Harvard Smithsonian.
Hello, everyone. It's encouraging to see that many efforts are being made to actually study interaction between the aerosol and hurricanes. So one of the primary questions that I'm trying to answer is that how much we were responsible for that formation of the rainfall by including a lot of anthropogenic aerosol into the atmosphere. So obviously we need a CTM model to be able to quantify this contribution in a deterministic way. We need to have an anthropogenic emission on and off. And also we require to have a weather model that is responsive to those aerosol changes. Because this sensitivity is very nonlinear, it heavily relies on the initial condition of the inputs. So we should make sure that the aerosol properties are right, the microphysics that we are using is actually responsive, and the initial condition of that physical properties of that hurricane is accurate. I'm sure you are all familiar with the two main effects between aerosol and cloud formation. When we have larger droplets, because we have lower vapor pressure and lower curvature, the condensation would be easier over that surface and evaporation becomes harder. So mathematically, you can see the vapor pressure over that curved area is inversely proportional to the radius. So we have a deep convection activity, and then we inject big dust particles, we facilitate potentially the condensation of the flux. In very low radius, this is not very effective. So we have soluble aerosols, and they have very low vapor pressure. So based on the equation, you can see that the radius has a power of 2.3 and has a negative value, which means in very low radius can significantly reduce vapor pressure and facilitating the condensation and releasing the latent heat flux. So they are actually more effective, especially in the low radius range. To get this information, so it's obvious that we need aerosol number, we need radius, we need solubility. And we got those information from GeoSchem Thomas. It has two independent moments. One is for beam sizes and one for masses. And we ran the model in two different scenarios, when anthropogenic emission is on and one is off. And we got all those mass per beam and also the total number of aerosol per beam from 3 nanometer to 10 micrometer for different type of aerosol categories. The microphysics that I'm going to use is actually summarize all this information through this empirical equation that the number of CCN equals to a fixed number and a supersaturation to power of the K. So it's important to translate this information from GeoSchem Thomas to be able to use that microphysics that I'm going to use. And a script is actually available on the GeoSchem website. We follow this paper. We provide the outputs from GeoSchem Thomas, and then it gives us the critical supersaturation ratio. Any ambient relative humidity above that critical ratio, we actually automatically convert the aerosol to the cloud droplet. So by changing the supersaturation ratio, we can fit that equation and calculate N0 and K for each grid cell, and then we can pass it to the microphysics. So to have an idea, like how many CCN we have when we have anthropogenic emissions on. So when the Hurricane Harvey actually made a landfall in August 2017, this figure actually, the left side shows with the number of the CCN under 1% supersaturation. You can see that there's almost nothing actually over Texas. And for that area, the yellow box actually calculated the CCN spectra. And you can see that the anthropogenic emissions were responsible for almost an order of magnitude of the CCN concentration over that specific region. So the differences are actually significant. And if you look at the spatial wise, you can see most of them are actually in Texas, located in western part of the Texas and the border with Mexico. For the weather model, we use WRF for 1 kilometer because we need to solve hydrostatic component of the model. And for the microphysics, we use spectra beam microphysics, which explicitly solve those hygrometers conversions. And of course, there are other like major configurations for the model, which I don't have time to go through, but we try to use the most well-documented options. And despite of using those, we were unable to reproduce Hurricane Harvey, so we had to resort to using a variational numerical data assimilation with asymptotes of our observation, including satellite, microwave, GPS occultation, and atmospheric wind vectors from geostationary satellites. And we are hoping when TEMPO is launched, we can supplement this information in future. And by having those assimilation, we'll be able to actually improve the forecast of the model to be able to solve that sensitivity. So when we ran the model without any nudging or any assimilation, any guidance, to control the first panel shows that we couldn't reproduce the track intensity accurately. When we nudge the model to reanalysis data, we are still struggling to make that intensity right, but with assimilation, we were able to get the best performance. When hurricane made landfall, after that, we freed the model from any constraints, so we were able to do the sensitivity with anthropogenic emission on and off. So if you see at the first two rows, you can see that when the hurricane made landfall at a as the center departed from the Gulf, more moisture loss over time. But it provided a mechanical mechanism that prolonged and fed rainfalls over Houston. And at that time, we can surprisingly see that the plume actually were carrying on from western Texas to that region over Houston when deep convection activities were going on. So this coincidence shows how important it is to have actually an accurate CTM model. And if we calculate the differences, the clean and polluted radius, the difference, the distance from the center of hurricane versus time, you can see the time that that plume came over Houston, we have up to 25% enhancement rainfall, evident enhancement of vertical wind and also rain mixing and liquid water content. Is showing that the latent heat will release and the updraft actually got accelerated. And that enhancement in vertical motion actually damped convection far from that rain band. So indirect effect actually just redistribute the moisture release over a large area. The whole precipitation value will remain constant. So the last figure shows that, okay, when we have a clean scenario and a polluted, you can see over Houston on domain-wise, the precipitation increased by 10%, which was closer to the satellite observation. And we attribute this to that polluted plume that coming from western Texas at the time that the convection activities were going on. So to wrap up, we found that the geoscans show a lot of pollution from western Texas. Is actually a place that TCQ is very interested, especially cities like El Paso. And both models, the weather and the CTM model together, they show that the time of that plume were coincided with actually the time that the deep convection activities were happening. So enhance the latent heat flood and updraft flux. And as a result, we got up to 25% more precipitation. So it's important in future we couple these models and show that the emission can actually sometimes worsen the severe weathers and show the other implication of the air quality. Okay, thanks for your attention. I'm happy to take your questions.
Okay, so you nudged your geology simulation. Don't you worry that you won't be able to fully get your aerosol back that way?
So after, so before the landfall, we tried to use the data assimilation to improve the initial condition. But after landfall, when the sensitivity started, we free the model from any constraint. So there is no nudging and no data assimilation to be able to see these impacts.
Yes. So you're showing you have you have especially when the particles are really hot. The thing with the problem have like
about the hydroaerosol?
I couldn't.
Or I mean, when you have anthropogenic emissions up, that can influence your boundary layer height. Do you have any idea why is that?
The boundary, we actually saw change in boundary layer height too, but of course, in future we need to have a high resolution model. I'm sure that that can also see those impacts too. But we saw change with PBL because that in 1 kilometer resolution, we can solve explicitly that non-hydrostatic components. So we also saw enhancement in PBL because of the more latent heat release and larger vertical motion.
Thank you. We have to move on. So,
Good morning. I am Ichi from UAF. I'm a postdoc working with Jingqiu now. The goal of this study is to use the observed trend of organic aerosol as a constraint to quantify the anthropogenic impact on biogenic SOA. The current model, the version 12, the complex SOA scheme, considers SOA formed from both the reversible partitioning onto pre-existing organic aerosols calculated by the VBS, the volatility basis set, and the aqueous phase SOA formation from isoprene products. On the right, I show the observed sulfate and OA summertime averaged over the Southeast US from the improved network. Both sulfate and organic aerosol are decreasing, and Moraes et al. Attributed this declining trend of OA to the reduction in anthropogenic emissions of SO2, which links to the sulfate aerosol volume and the aerosol acidity, which are important for the aqueous phase SOA formation. Here I show the comparison between the model and the observation, the total OA. There is no trend in the primary OA or the dry SOA formed from the VBS. Both the modeled magnitude and trend are dominated by the aqueous phase SOA formation, and mostly from the IPOCs here, the blue shades. The model overestimates the downward trend of total OA. And also the model overestimates the contribution from isoprene, which accounts for 58% in 2013, much higher than the suggested values from the these two observational-based analysis. So these are the JJA average. If we break it down to see the monthly data, we see another major discrepancy between the model and the observation. The model shows a large month-to-month variation, like 10 years ago from 2005 to 2007. The brown line there, the August value is almost 2 times as much as the June value, which is not seen from the observation. I checked a few variables like the precursor, the isoprene emission, and the sulfate aerosol, which provides the aerosol surface for the IPOX uptake. But the key is the aerosol acidity, the hydrogen ion concentration here. So why the acidity is such high in August in the early years? It's likely linked to ammonia. Ammonium, its emission in August is much lower than June and July. Here I plot out the monthly data of modeled ammonium, IPOX, SOA, and sulfate here. In the early years, when sulfate is still high, the insufficient ammonium in August leads to high aerosol acidity that leads to the high IPOX SOA, which dominates that large difference between the June, July, and August there. And so we see a strong anti-correlation between the IPOX SOA and ammonium. Right here, like R square is much higher than the years later. So later, when the sulfate has been reduced, ammonium becomes sufficient, and we see a much correlation between the two. So the model is wrong about this month-to-month variation. There could be 3 possibilities. Either the IPOX SOA is too sensitive to the H+ concentration, or the acidity is wrong in the model, or we overestimate IPOX SOA in general. So what I did to resolve this issue as the first step is to implement a coating effect for IPOX uptake. Here I did a simple linear scaling to consider a strong coating effect. And here I show the results. With organics coated outside the sulfate aerosol, it will reduce the heterogeneous reaction probability of IPOX uptake, the gamma value here. Here, the x-axis is the organics mass fraction, and y is the H+, the acidity. So without considering coating, gamma will be independent of this organics mass in the total aerosol volume. And gamma increase quickly with aerosol acidity here. But with considering this coating, it will reduce both the gamma value and the gamma sensitivity to the aerosol acidity. I also implement a more physical and complicated coating scheme, and that results are kind of between the default, the no coating one, and the linear scaling one. So here I only show the results. I only show the results for the linear scaling. I did a third simulation by fixing the H+ concentration as a constant. I did this because the model predicts a decreasing trend in this 10 years in the H+ concentration following the reduction in sulfate. But there's still a lot of debate on that. Some other studies saying that the aerosol acidity either remains unchanged or it could increase a little bit. So I did this third simulation as a sensitivity test. And here I show the results. The default model overestimates the downward trend of total OA. With implementing this coating effect for IPOX uptake and further fix the H+ concentration, they will the simulated OA trend is better compared to the observation. And this too will also reduce this large month-to-month variation, which is unrealistic. And so here is my quick summary. The current model overestimates the 10-year trend of total OA, and it's very likely that we overestimate the impact of anthropogenic SO2 emission reduction. Still, the model may overestimate the contribution from IPOX, but underestimate monoterpene chemistry. So that would be my next step to update the monoterpene chemistry based on new findings from the lab and field. And thank you. I would like to take any questions.
So your hypothesis is that this 10-year trend, the overestimated trend is the overestimation of IPOX SOA. But I noticed that around 2011, there's a interaction variability that the model is really capturing really well. It seems to be driven by isoprene emission.
Yes, that's true.
Use that to test your hypothesis, whether the response to isoprene during that interaction variability period is correct.
We may probably do that if we divide it by the total isoprene emission to see the ratio as a standardized emission efficiency and see the IPOX. Yeah, that might be helpful. We haven't done that yet, but yeah, that would be.
I could add 2011 is a drought year. So
yes, so the temperature is high and isoprene is high.
Or maybe underestimate. So that's uncertain then. So that's why the 2011 stands out. And the observation also shows it. Yeah. So fire.
Well, the drought year will stimulate isoprene emission, so the isoprene emission is high in 2011.
Other questions?
I think the southeast US is a very sensitive region in about the ammonia to the sulfate ratio. So, when the sulfate is higher than the threshold, and the low ammonium in August will lead to very high aerosol acidity.
Did you look at why the ammonia is so much lower in August compared to June and July?
That's from the emission inventory. I think we used the NEI emission inventory, and that did show a low ammonium emission. And before that, June and July is high because the temperature is high and the agriculture activity, there's a lot of emissions from the fertilization, etc. But in August, there is a lower emission. But the difference between the June, July, and August is larger from the NEI emission inventory compared to other inventory. We've looked at that.
Thank you, Yiqi.
Okay, thank you.
Next speaker is Yi Wang from University of Iowa. I'll do an inversion of SO2 and NOx.
Good morning. I'm Yi Wang from the University of Iowa. My topic is using satellite SO2 and NO2 observations to optimize the emission inventory over China and apply the optimized emission inventory for improving air quality forecast. Over the past 20 years, many satellites have been launched to observe the atmospheric compositions, including SO2 and NO2. Of these sensors, ARMS is relatively new and will continue providing SO2 and NO2 observations in the next 10 to 20 years. But we are interested in using ARMS SO2 and NO2 observations to optimize emission inventory and then apply it to improve air quality forecast. Here, due to the time-like bottom-up emission inventory, there should be a difference between GeoScale simulation and the ARMS observations. Then we use GeoScale, a joint model, to adjust the emission inventory until the difference between simulation and observation is small enough. Then get to optimize the emission inventory. Then the OMI observations are used for validation. Here, to save computational time, the inverse modeling is conducted at coastal resolution. Then we use the VSNet light or the prior fine resolution emission inventory to downscale the coastal resolution emission inventory. Then use it for forecast and validation. Here is a case study for October 2013. The applied emission inventory used here is the mix for 2010 due to the time lag. We can see posterior SO2 emissions is about 36% smaller than applied emissions. For NOx emissions, it also shows a decrease. Then both the prior and the posterior emission inventories are used to simulate SO2 and NO2 vertical column densities to compare with ARMS observations. Compared with ARMS observations, for the prior simulation, SO2 is much smaller, much larger than OMI observations. And for posterior simulation, it's become much better with much small bias. For NO2, we can see that the posterior simulation also show improvement. As I mentioned, the inverse modeling is conducted at a 2 by 2.5 degree coastal resolution to save computational time. However, the coastal resolution emission inventory cannot be used to simulate or forecast surface SO2 air quality. Surface SO2 simulation in the coast grade smear and cannot capture the high concentration of SO2 close to sources. Thus, we need to downscale the emission inventory. Here, we assume the a prior fine resolution emission inventory has the correct spatial distribution, but bias exists. Then we use the spatial distribution to downscale the posterior coastal resolution emission inventory to the fine resolution posterior emission inventory. All these fine resolution emission inventories are used to simulate surface SO2 and validated with in situ observations. We can see apparently the posterior simulation has much better results with small bias and small root mean square error than the prior simulation. For the similar reason, the NOx emissions is also downscaled according to the spatial distribution of the prior fine resolution emissions. Get the fine resolution posterior results. For another thing, we can see here is the choke-omi vertical NO2 density, and here is the Weir's nighttime light. They have good correlation. So another method is use the Weir's nighttime light to downscale the NOx emission inventory. Get another downscale emission inventory. Yeah, all this are used to simulate NO2. We can see for both the downscaled results for both the posterior simulation, they have better linear correlation and small root mean square error compared with a prior simulation. Here, the emission we have optimized emission inventory. Then the problem is that how to use it to improve air quality forecast. The idea here is simple and useful. The optimized emission inventory of current months is applied to next month to forecast. Here, the case is for inverse modeling case is for October 2013. Then the optimized emission inventory is applied to the November 2013 as a posterior forecast. As a for validation, we also use the prior mixed emission inventory for 2010 October to simulate SO2 and NO2 as the prior forecast. We can see for the posterior forecast SO2, it has a small bias and a small root mean square error compared with the prior forecast. For NO2, we can see that the posterior forecast also show improvement. All the emission modeling here is conducted at a monthly scale. In the near future, several geostationary satellites will be launched and will providing hourly observations. So it's very promising to using the hourly observations to constrain emissions at a better temporal resolution, maybe daily. So the main conclusion is we use satellite data to constrain emissions at a coarse resolution, then downscale to fine resolution to improve simulation and forecast. The research is funded by NASA. Thank you for your attention.
Why doesn't your approach improve the spatial consistency with the observations? Your correlation coefficient doesn't change much.
For NO2, here it only shows the bias changes become much better, but for linear correlation, we cannot see improvement. I think one reason may be the data quality of the SO2 observation. Maybe for different regions, the data quality varies. Maybe I'm not sure.
I was curious, there seems to be some really high in situ SO2 concentrations that maybe have a difference with satellite columns of SO2, and I was wondering if you could comment on that.
Do you mean for some sites the validation is not so good, right?
I mean that it seems like the satellite observations are suggesting you really need to ramp down SO2 emissions, but then you're missing some of the more extreme ground level SO2 that's observed. So I was wondering if maybe there's something with translating the satellite to the surface.
Sorry, I didn't get.
about
Emissions.
the model still did not capture the peak in the surface SO2 observation, right?
Yeah, but it seems like the satellite doesn't see that really high surface SO2.
Yeah, I think this is the problem of the resolution. If we use a high temporal resolution, high spatial resolution simulation, maybe we can capture. Another problem is I think you see some regions. I think for these regions, I compared the observations for arms is usually on larger than ohms, but for this region, it's smaller than ohms. So I still think it's a problem of data.
Thank you. Let's thank Yi again. Last but not least, we have Jun Mao from Dalhousie. Topics a source attribution of particulate matter for Canada using geoscan.
Thank you, Professor Wang. So today I'm going to talk about the source contribution to PM2.5 in Canada. PM2.5 has been recognized as the leading environmental risk factor for mortality according to global burden of disease. It can cause a chronic respiratory disease, cardiovascular disease, and even lung cancer. For Canada has a low level PM2.5. However, studies still report the adverse effect of the long-term exposure to such low-level concentrations. And also, half of the Canadian population lives at the PM levels at which GBD still don't know the health effect. So sectoral contribution studies are needed for the future air quality management and the association with its health outcome. So in this study, we conducted nested grid baseline and sector sensitivity simulations using geoscan. We include detailed anthropogenic emission inventories for Canada and the States. And we use global fire emission database as a wildfire inventory. We studied the power generation, agriculture, industry, residential combustion, transport, and wildfire sectors. We also include natural emission sectors such as volcanoes, mineral dust, and biogenic SOA. We downscaled our simulations using satellite-derived PM2.5 dataset. And the plot on the right panel shows that our downscaled baseline simulation is highly consistent with the ground-based measurements. This plot shows the spatial distribution of the contribution from individual sectors to the total PM2.5 over North America. And the wildfire on the top left corner has the largest contribution over Canada at the west of the states. The transport sector has the largest contribution over populated regions. The residential combustion has the largest contribution over southern Quebec, Great Lake regions, and the northwest and northeast United States. The industry has the largest contribution over industrial regions such as Alberta, Canada, California, and Texas. The agriculture has the largest contribution over Alberta, Canada. Both the biogenic SOA and power generation has the largest contribution over Southeast United States. The other sectors such as CSOT, mineral dust, and other sources, which include volcano, long-range transport from other continents, and the DMS from the ocean, has a small contribution to the total PM2.5. The bar chart here shows the sectoral contribution to the population weighted average PM2.5 in Canada in the different regions in Canada. So annually, the wildfire in red is the dominant contributor in Canada, followed by transport, which is shown in brown, and then followed by residential combustion in gray. And this relative importance of a sector contribution will vary over regions. For example, in central Canada, the leading contributor is residential combustion, while the other regions are wildfires. The hatched bar here shows the contribution from the US sources, and mostly from agricultural and power generation sectors. And this contribution will also vary over regions. It has the largest contribution over Central Canada. I look at the sector contribution in summer, which shown on the left panel, and winter in the right panel. And wildfire has the largest influence over all the regions in Canada in summer. And residential combustion has the largest, is the leading contributor in Canada, except the Western Canada and Northern Canada. And also the contribution from the states is different over regions. It's around 12% in summer and 46% in winter. I also investigate the trend of the sectoral contribution over the last 3 decades. And the fraction of the anthropogenic emission sectors decreased from 80% in 1990 to 58% in 2010, reflecting the large anthropogenic emission reduction over those 3 decades. And also the wildfire has a larger contribution over the most recent decade. To conclude this, annually wildfire has the largest contribution over Canada, followed by transport and residential combustion. But this relative importance of the sector will vary over regions and seasons. And also around 30% annually, the population weighted average PM2.5 are from US sources. And this contribution will also change over seasons and regions. This is all I have today. Thank you for your attention. And I'm going to take some questions.
Yes.
So when you came to calculating the total contribution from all sectors combined, was that calculated using a separate simulation where you zeroed out all sectors simultaneously? Or did you just add up the deltas that you got from each individual simulation?
So we did separate simulations for each sector.
I'd be curious to know if you got the same answer if you zeroed out all sectors simultaneously in terms of your total contribution from anthropogenics. Our result of simulation suggests you wouldn't.
That's very interesting. Actually, we found in our method there's like large nonlinear relationship in the atmospheric chemistry. So probably.
And then you can sort of dig into this question of sectoral interactions, which might change some of your answers.
Yeah, thank you.
Daniel?
Yeah, what about the Asian pollution influences?
Yeah, we include like the long range transport, but so here I show I include that or in the other sources. But we kind of don't know how to interpret. We just include everything in that sector, which is like long range transport from all other continents. So we didn't separate the from Asian.
Is the biogenic SOA dominated by monoterpenes? And if so, our potential underestimating monoterpenes, would that impact the biogenic contribution that you have now?
That sector, according to our research, is dominated by the SOA. I have so in my simulation, I use your scheme, but I'm not sure if it's from ethanol. Thank you.
Any other questions? If not, let's thank all the speakers. Thank you.
Thank you, Yushan. Thank you for chairing this session. Okay, so please enjoy the coffee break here, and afterwards we're going to vacate this room, and we're going to move to Maxwell Dworkin for our clinics. So we're going to have 2 rounds of clinics. The first one looking at GSCAM on the AWS cloud, and the second one, GSCAM and Earth system models for half an hour. And then after that, we'll have another half hour of clinics on the nested model and on the joint model. And also we will have a side session on the GSCAM benchmarking process and whether we should, how we should improve it, and then we'll be in Pierce Hall 100F. This is all indicated on the agenda. After lunch, we'll reconvene at 1 o'clock, not 1:30. 1 o'clock, so that we can be done by 2:30. And again, it will be a natural Dworkin, and we'll be going over the model development priorities and so on, and address any concerns that the community might have going ahead. Get your feeling on all of this. We will have after that AWS Cloud Workshop, which will really be hands-on. Again in Maxwell Dworkin, and then the GSCAM Steering Committee will meet in Pierce 100F this afternoon. Actually, for the Steering Committee members, right now I have it starting at 3 o'clock, but I know a few of you have a plane to catch, like at 3:30 or so. So let's start at 2:45 if we can. Pierce 100F. Okay, enjoy the coffee break, and then go on to the clinics. And